Chapter 7, Partial Differential Equations. An ordinary differential equation is one with ordinary derivatives of functions of a single variable each, time in many applications. These typically describe quantities in some sort of lumped parameter way. Mass as a point particle, a spring's force as a function of time varying displacement across it, a resistor's current as a function of time-varying voltage across it, etc. Given the simplicity of such models, in comparison to the wildness of nature, it is quite surprising how well they work for a great many phenomena. For instance, electronics, rigid body mechanics, population dynamics, bulk fluid mechanics, and bulk heat transfer can be lumped parameter modeled. However, as we saw in Chapter 5, there are many phenomena of which we require more detailed models. These include detailed fluid mechanics, detailed heat transfer, solid mechanics, electromagnetism, and quantum mechanics. Those are just a few of them. In many cases, what is required to account for is the time-varying spatial distribution of a quantity. In fluid mechanics, we treat a fluid as having quantities such as density and velocity that vary continuously over space and time. Deriving the governing equations for such phenomena typically involves vector calculus. We observed in Chapter 5 that statements about quantities like the divergence, for example, continuity, can be made about certain scalar and vector fields. Such statements are governing equations. For example, the continuity equation. And they are partial differential equations, PDEs, because the quantities of interest are called dependent variables, for example, density and velocity. They're both temporally and spatially varying. Temporal and spatial variables are therefore called independent variables. In this chapter, we explore the analytic solution of PDEs. This is related to but distinct from the numeric solution, i.e. simulation of PDEs, which is another important topic. Many PDEs have no known analytic solution, so numeric solution is the best available option. However, it is important to note that the insight one can gain from an analytic solution is often much greater than that from a numeric solution. This is easily understood when one considers that a numeric solution is an approximation for a specific set of initial and boundary conditions. Typically, very little can be said of what would happen in general, although this is often what we seek to know. So despite the importance of numeric solution, one should always prefer an analytic solution, if you can arrive at one. 3 good texts on PDEs for further study are Kreisig. I like Kreisig's Chapter 12 on it, Strauss, and Haberman. I think that the other two are certainly much more complete texts on PDEs. They're both quite good. Maybe my preference is the Haberman one, but Strauss has some good things in it too. I would say that things to watch out for in Kreisig are that Kreisig is really trying to give you a taste or a feel for PDE solutions and is not treating PDE solutions in general. There are a couple techniques that we'll see, that we'll develop in the coming lectures, are used by the Kreisig text, but they're not sort of introduced in any general systematic way. So it can kind of feel like, ooh, here's a PDE, here's how to solve it. Here's a PDE, here's how to solve it. But there's no like general technique. There is no general technique that works for all PDEs, but there are certain solution techniques that do work for classes of PDEs. So that's what we'll talk about. And the other texts are much more thorough in that they develop more general procedures and discussion of the different types of problems that can arise. So, yeah. All right. So that is the intro to Chapter 7 on PDEs.